Final exam review, extra questions that I modified for 2024. Eagle clutching a fish, following an altitude of 60 meters at a horizontal speed of 8 meters per second. When spook drops the fish, how far does the fish move horizontally as it falls to the ground? All right, so I guess I better draw a bird or something. Oh boy, rough. Not a great drawing. Anyhow, what you got to realize is the initial speed of the fish is the initial x is the same as the bird, 8.0 meters per second. So what I'm going to do is projectile motion. 1, 2, 3, 4, 5. All right. You got to remember in projectile motion, there's no acceleration. And no acceleration in the x direction. In the y direction, there is acceleration, and it's due to gravity. It's negative, I'm going to do negative 10 meters per second squared, because as something falls, the only force acting on it is gravity. All right, little side calculation here. The only force acting on it is the force of gravity, which is mg. So if it's falling, it's accelerating down, right? F net equals ma. All right, F net in this case is just mg trying to pull it down. I guess it's negative, I'll say, equals ma. M's cancel out. We get A is equal to negative G. So, all right, 10 newtons per kilogram is the same as 10 meters per second squared. Just a little proof of projectile motion. So your x velocity is 8.0 meters per second. The altitude, that's how, it's going to fall down. Delta y as it goes is going to be negative 60 meters. It's going to fall from that height. It's going to go in a trajectory like this. We're looking for a delta x. So we go over here, negative 60 meters is the change in height. The initial y is 0 because we're launching it horizontally. So I'm going to use El Grande in the y direction. All right, initial y is 0. T is 2 delta y divided by ay, square root of that. Do the algebra, that's where you end up. 2 times negative 60. I already listed the variables up here, so I don't need to put them in down here. Divided by negative 10, we'll go second square root of 2 times negative 60 divided by negative 10. I could just leave this negative signs off of there. We get about 3.5 seconds. So then we take that and we put it in here. Delta x equals Vx times t. It's really El Grande, but again, the A is 0 this time. So delta x is 8.0 meters per second times 3.5 seconds. We get about 28. Delta x is about 28 meters. Okay, there's the first extra problem. Second extra problem, this is a good one. Force diagram, all right. Classic, this is 55 degrees here. It tells us this right on the thing. This is pointing this way. We'll call us FT1, we'll call us FT2 equals positive 300 newtons. We want the tension in the angled rope. We've got gravity. We know the angle and we know this tension. So the tension in the angled rope. Well, what's going on here is I'm going to redraw it over here. We got 300 this way. We've got that tension. We've got gravity. FG 300 newtons that way. FT1, FT2. All right, FT1's x component has to be equal to 300. So FT1 x component has to be 300 newtons. Well, actually, it would be negative, right? Because it's going that way. So these two forces have to be balanced. So if we look at our triangle here, we've got 300, and I don't put the sign on our little triangle drawing because we're just trying to figure out the hypotenuse here, 55 degrees. So cos of 55 degrees equals 300 over FT1. Right? The length of that side of the triangle is going to give us FT1. Cos of 55. Solve for FT1, so FT1 equals 300 newtons divided by the cos of 55 equals, 300 divided by the cos of 55. It's going to give us 520 newtons. I'm just going to do it to 2 sig figs. So now we know that's 520 newtons. Now, to determine the weight, force of gravity, well, I don't know the mass, so I can't just do mg. What I have to realize is Fg has got to be equal in magnitude to Ft1y. And sometimes we put absolute value signs around these things. That sometimes can help. So force of gravity has to equal magnitude of Ft1y. That's the that's this side of the triangle. So that's the opposite side. So I'm going to use this triangle. I'm going to say tan of 55 equals Ft1y divided by 300. Opposite over adjacent, TOA. So Ft1y equals 300 times the tan of 55. 300 times tan of 55. That gives us 428 newtons. So the weight, which is the magnitude of the force of gravity, is then Fg equals 428 newtons because Fg has to just equal Ft1. So that's a really good problem. Guarantee there's one like that on the midterm. Angled force has 2 components, we call those. The components balance out the for other forces. All right, almost done. Let's see here. We've got, this was an extra question I added. Took out the one gravity thing, and I said, you know what? I need a gravity question. So an asteroid with a mass of 5 times 10 to the 4th orbits a planet. Mass times 10 to the 6.2 times 10 to the 23rd. So we got a planet. We've got an asteroid. It's in a circular orbit. Great. So that means it's going to have an Fg. They both experience that force of gravity. All right. Radius here. It's got an orbital radius. That's r. Its velocity is that way. Tangent, of course. All right. Determine the force of gravitational attraction between the asteroid and the planet. All right. Fg equals g m1 m2 over r squared. Pretty straightforward. G is 6.67 times 10 to the negative 11th newtons times meter squared per kilogram squared. That you can get off the front of your reference table. M1 and M2. Okay, we'll do the planet, 6.2 times 10 to the 23rd kilograms. We'll do the asteroid, 5.0 times 10 to the 4th kilograms. It's like 50,000 kilograms. It seems like a pretty decent sized asteroid. Radius is 3.0 times 10 to the 7th meters. So pretty darn far. Oh, about 30 million meters. All right. So 6.67 double E negative 11 times 6.2 double E 23rd times 5 double E 4 divided by 3 double E 7. Oops, I almost messed that up. I gotta go back, put parentheses around this, right? So just so you can see what I'm typing in my calculator. All right, I gotta go back and do 3 double E 7, close that parenthesis, square it, and get about 2,300 newtons. Very cool. All right, orbital velocity of the satellite assuming a circular orbit. All right, since it's in circular orbit, the net force acting on that satellite we're talking about, right? So let me just do like just the satellite itself traveling in this circular orbit. There's its V. FC pulls it towards the center of the circle. At the center of the circle is that planet. right? This planet down here. So F net equals mass times centripetal acceleration, which is mass times velocity squared divided by radius. And keep in mind, this mass is the mass of the satellite. So the net centripetal force is coming from gravity. So that number is going to go in for F net C. So let's put it all together here. We're going to have 2,300 newtons equals mv squared over r. I'm looking for r, right? So I guess I'm just going to have to plug the numbers in here at this point. 10 to the 4th kilograms times, or sorry, I'm not looking for r, I'm looking for v. So raise 3.0 times 10 to the 7th. I should have just done this in terms of variables first. So we got to multiply, got to basically cross multiply here, right? So we get V equals radical 2,300 newtons times 3 times 10 to the 7th meters divided by 5 times 10 to the 4th kilograms. It's radical. I brought this one upstairs, brought this downstairs, take the square root of it. That'll give me the final answer. So in my calculator, I'm putting second square root of 2,300 times 3 double E7 divided by 5 double E4. We get 1,200 meters per second for our orbital velocity. Very good, very good. I like that one. So one last extra question here. And I'm just going to put these as a second PDF in the solutions. And the reason I'm shooting a video is because I did find other videos of me writing up the solutions to the other parts. So a particle with a charge of 0.1 nanocoulombs accelerated through a potential difference of, so Q is 0.1 times 10 to the negative 9th coulombs. V is 5,000 volts. We're looking for the work done. All right. And then how fast would it be moving? Okay. Not enough space here. I apologize for that. So work equals QV. That's right off the equation sheet. So the work done is going to be 0.1 times 10 to the negative 9th coulombs times 5,000 volts. 0.1 double E negative 9 times 5,000 gives us, oh man, 1, 2, 3, 4, 5, 6, 7. Because 5 times 10 to the negative 7th joules. All right. The other thing I didn't tell you was, let's assume it started from rest, right? So remember, work equals change in kinetic energy, which is KE final minus KE initial. So that one's 0. So 0 or 5.0 times 10 to the negative 7th joules equals 1/2 of 0. Oh, now this is the trick. I gotta change that to kilograms. 0.001 divided by 1,000 is 1, 2, 3, 4, 5, 6. 1.0 times 10 to the negative 6 kilograms times V squared. So that's the trick, right? The fact that you gotta convert that to kilograms, that's annoying. You just gotta move this another 3. But now multiply both sides by 2, divide both sides by 1. Okay, so V is going to be the square root of 2 times 5 times 10 to the negative 7th divided by 1 times 10 to the negative 6th. So second square root of 2 times 5 double E negative 7 divided by 1 double E negative 6. 1.0 meter per second. Didn't mean to do that, but that's kind of funny. All right, that's it for the extra problems.